So hypothesis testing is at the heart of many scientific endeavors in many fields like social sciences, and medical research. Also, an important example of these studies usually include testing if two features are correlated or independent. For example, if obesity is correlated with heart disease or it's independent. Or another example is that if the salary is independent of gender or not. Often in these studies, we are working with individuals' data, so we prefer to have algorithms that preserve the privacy of these individuals. Let me try to explain our problem and set up more formally. We're focusing on the independence testing problem. We have a distribution over a two-dimensional domain, and we receive a list of pairs, xy's, from as samples from this distribution P. And our goal is to test whether x and y are independent from each other or not. So the null hypothesis, or the H0 hypothesis, is x and y are independent, and we are trying to distinguish this case from the other case that X distribution P is alpha far from any independent distribution Q. So this is corresponding to the case that alpha is small enough, so we don't care about the in-between cases. Like if something is, like, think of it as epsilon close to some independent distribution, it is okay for us to declare it as an independent pair. It turns out this problem is equivalent to another problem, which is called closeness testing, which we try to test if two distributions that we have sample access to are equal or far from each other. In this case, for the independence testing problem, if P is independent, P should be equal to the product of its marginal. And if P is theta of alpha far from its product, the product of its marginal, then it will be also far from being independent. So this closeness testing problem is actually at the heart of several other problems, or closely related to other problems. For example, testing uniformity, which is a special case of closeness testing, or testing to equality to a known distribution. It is also the techniques that is used in closeness testing has also appeared in several other testing problems, like mixture testing and testing K-histograms and so on. So we are for the purpose of this talk and this work, we're focusing on this sort of more general problem of closeness testing. The setting is as follows. We have two unknown distribution P and Q over a discrete domain of size n. We receive samples from these distribution, and our goal is to design a tester or an algorithm that with high probability can distinguish the following two cases. If P and Q are equal, we want to output accept, and when P and Q are alpha far from each other, we want to output reject. So I'm not going to define differential privacy for this crowd, but our setting is central differential privacy, and we consider P or DP. The goal is to design a differential private tester with optimal sample complexity that uses as few samples as possible, basically. So Adam Gross gave a talk this morning, which was very interesting. I just want to, because it was on a very similar topic, I just want to highlight the differences of our setting and what I understand from his talk. So we have the main assumptions that we are making in this work is that the domain is discrete. So we have a discrete domain of size n, which is true when you have non-numerical features, or you have features with certain accuracy and bounded. What this assumption basically buys us is that it led us to have an algorithm that works for any distribution. So we are not making assumption about the underlying distribution, except that it's discrete over n. We are able to provide a sample complexity and assure that for that certain number of samples, we have both type 1 and low type 1 and type 2 error, meaning that the probability of false negative and false positive both are very small. And also, it's a non-asymptotic sample complexity. To be more precise, what this means is that for a given n, the domain size, alpha, the proximity parameter, and epsilon, the privacy parameter, we come up with the exact number of samples that we need to use up to constant factors. And we're not considering the case that in some work you see that the behavior of the tester is studied when the number of samples goes to infinity or in the limit, basically. So let me briefly explain our result. The contribution in this work is we make a specific closeness tester private. It's called a flattening based tester. I will explain what this tester is. But the main property of this tester is that it uses the structural assumptions about the underlying distribution. So actually, when we use the reductions to other problems that I explained earlier, it can actually guarantee optimal sample complexity for those other problems. So if we want to get optimal sample complexity for other problem in the non-private case, like at least we should be optimal in the non-private case, we need to make this tester private. And by privatizing this tester, we will be able to get basically private tester for other properties for free. I mean, not quite free, but close enough. Using our techniques, we provide an algorithm that uses this many samples for independence testing. And we also were able to provide a new algorithm for distribution testing with closeness testing with unequal size sample size. So we have different number of samples from P and Q. And we also were able to get tighter results for the other problems. Our sample, the 4 terms you see in the sample complexity, the first 2 terms are basically the cost when we have no privacy, and these are tight and optimal. The second part is the cost of privacy, and we are tight up to those red terms that you see. This problem and a closely related problem have been considered in the literature. By no means this is not an exhaustive list, but these are just few examples of the works that studied similar problem. And let me talk about what our techniques, and first I will start by what the flattening based tester is, and then I will explain how we make that private. At the heart of this closeness testing, there is this statistic Z. In this definition, Xi and Yi's are the frequency of the ith domain element from the 2 distributions. So in the sample sets from P and in the sample sets from Q. It turns out the sample complexity of this statistic is proportional to the maximum L2 norm of P and Q. So if I have 2 distributions that they have low L2 norm, this would be a very efficient algorithm. So the way that this tester works is it takes 2 arbitrary distribution P and Q, but potentially high L2 norm, and it creates a mapping to map this distribution to 2 other distributions, P prime and Q prime, such that the L2 norm of P prime and Q prime are low. And this mapping is designed in such a way that it doesn't change L1 distance. So if there were 2 distributions that we start with are equal, they will remain equal. And if they were alpha 4 from each other, they will remain alpha 4. So the flattening basically refers to this mapping. The way that it works is that we have a distribution P. We know that the elements that contribute largely in the L2 norm of the distribution is the large elements, like the elements with high probability. We draw samples, and using those samples, we detect what those large elements are, and we divide it into smaller sub-elements. And in that way, we basically reduce the maximum probability in reducing the L2 norm of the distribution. And we call the set of samples for determining this mapping as the flattening sample set. And the frequency of each element in this sample set determines on how many parts we are going to divide that element. So the structure of the new algorithm, flattening-based algorithm, would be like this. There are flattening samples. We use them to come up with the mapping. And then we draw new samples that are called test samples from P and Q. We use the mapping to map those samples to samples from P prime and Q prime. And then using the statistic that I showed, we will test if P prime and Q prime are equal. Okay, so I'm gonna move this one so you can see what is below this. Okay. So the issue, the main difficulty basically to make this approach private is that if you change one sample in the flattening set of samples, it totally changes your mapping, and it basically results in a very high sensitive statistic. And it's obviously it's hard to make high sensitive statistic private. So the goal is to come up with an approach to reduce the sensitivity of this statistic. Sorry, I have hidden some of the slides that they show up here. Yes, so if we change one sample in the flattening sample, it results in high sensitivity. But if we change one sample in the test samples, it doesn't change our statistic by that much. You can actually show that this part is okay. So our approach is that instead of using a fixed permutation of the samples, we try all permutation of the samples and use the first part for the flattening and the second part for testing, and compute the statistic for each of these permutation and take an average over the results. And this average would basically be our new statistic, which help us to determine if P prime and Q prime are equal or not. I'm not going to explain the details of the analysis, but basically our analysis has three main parts. First of all, we need to show that Z bar is still a good statistic for this problem. It still helps us to figure out if P prime and Q prime are equal or not. We also need to bound the sensitivity of this statistic in showing that using Laplace method, we can make it private with Laplace method of small magnitude. And then we also need to show the efficiency of our algorithm, both in terms of sample complexity and time complexity. So although I mentioned that we try all permutation, we can't actually try all permutation in a polynomial time. So we basically try to explicitly compute the contribution of each element in the statistic separately and try to avoid an exponential time complexity. And with that, I will conclude in thank you.